Okay, so for question 1, the homework. This is not working. Oh, I see. Okay. All right, having some technical hiccups here. Okay. Let's try this. Okay, that's working. Sorry about that. So, question 1. This is basically a question. The intention with this question was to like give you a bit of practice with the definitions of these stochastic environments and partial maps. And I guess the question itself was sort of geometric in nature. That give a bit more insight. So the question itself was to look at spaces of stochastic environments of a finite time in certain small cases. Because the small cases were the set of observation just having 1 or 2 elements, set of actions having 1 or 2 elements, and the time being just 1 or 2 time steps. So I think most people figured out that the easiest case was if there's only 1 observation, then basically all an environment can do is to just output that observation, and it doesn't matter if it's stochastic or not. There's only 1 environment. So in this case, I guess the space is just a single point. So I guess the next simplest case is when we have 2 observations. Let's call them 0 and 1. And let's say there's just 1 action and 1 time step. So in this case, the definition we had was taking a string of observation actions, either length 0 or 1. So I guess t is equal to 1. So this is just 1 here, and having a partial map here to distributions on O. I think a number of people forgot that this was a partial map, and I tried to explain why that's important. So, but we can start with taking entire maps. So if it was not just not partial maps, but entire maps, then it would require, I guess, delta O in this case is just the interval, because distributions between 2 points, it's just you can specify the probability of one of them. And then here, we need to specify eta on the empty input, and then we need to specify eta on a given observation O. And since there are 2 possible observations, I guess eta 0 and eta 1. So we need to specify 3 real numbers here. So if this definition involved entire maps, then we would just get a cube in terms of what the space is. Very good. cube like this, where let's say this direction is what eta on the empty input is, and then let's say vertically up is eta on 0 and horizontally is eta on 1. But then, yeah, if you take a closer look, let's say what the corners are. Like this corner would be something which is 0 on the empty input, and then 0 on observing 0, and also 0 on observing 1. While this corner would be 0 on the empty input, 0 on observing 0, and 1 upon observing 1. But basically, this is redundant, and this is the reason we were looking at partial maps, because we don't need to specify this entry of like what would the observation be if the previous output was 1, because in this case we know that the first output was 0. So basically, these two vertices should be identified, and similarly, these two vertices are going to be identified as well. And on the back face of the cube, we have a similar situation where, let's say, this vertex would be 1 on the empty input, and then how did I set it up? Say 1 on the output 0 and 0 on 1, and then, but then, for example, this vertex here would be 1, 0, 0, and here it's kind of the opposite way. We're specifying what would happen on if the first observation was 0 is unnecessary. So in this case, it's CLOS2 directive. In this case, it's these vertices that would need to be identified. So basically, what happens is that in these partial maps, on the front and back face of this cube, for the entire map, we specify an entire face, but actually, because these are only partial maps that are defined on the things that actually happen, those should only be intervals in the front and the back. So if I draw this over here, let's say this is the front of the cube, now just collapse into a single interval. Let's say this is the back of the cube. It's collapsed onto the. Actually, I should have drawn this the other way around. We collapse the front to just specifying this axis of what happens on when we observe 0, and the back we specify what happens when the observation was 1, and then basically the rest of the cube stays the same, so we can complete this, and we end up with this space, which is it's a tetrahedron. Does this picture make sense to people?
So am I getting it right that like because like the set of partial maps also contains entire maps, right? Or does it not?
No, it's partial maps. There are fewer of them, or like less information contained in them. So basically, that's why the entire maps contain extra information that don't need to be specified for the partial maps. So we get sort of it's a quotient. We kind of take a quotient of this where we forget some of the information.
So does it mean that when we are talking about like Calc E subscript S, like the set of stochastic environments, then every stochastic environment in this set is strictly partial.
Not every map is strictly partial, because if we let's say we look at this middle part, like the middle slice, which is at when the first output is 1/2, that one is still, it actually remains the same. So those are entire maps here. So we basically only need to collapse parts of the faces of this cube.
Okay.
Yeah, it's to do with deterministic choices in the history. So whenever you make a deterministic choice, there's a whole future that never happens. So it's just not defined.
Yeah, basically, if you're certain to output observation 0 in the beginning, then you don't have to specify the counterfactuals of what would I have output if the first one was 1, because that just doesn't happen. And then this way, actually, the vertices that we end up with here are just going to be, we just have to specify what the first and the second output is. So and in this case, we have 0, 0 here, and then 0, 1, and I guess 1, 0, and 1, 1. So the vertices are actually just exactly the deterministic environments. And that's going to be a general phenomenon, that the kind of extremal points of the stochastic environments are exactly the deterministic ones, which are okay. Any question about this so far? So in this case, we can, I guess, I was asking what the number of vertices is. It's going to be 4 in this case, and the dimension is 3. So notice that the dimension is the same for the space of entire maps and the space of partial maps, because on the interior we're not collapsing anything, but the number of vertices here, there are kind of more vertices than deterministic environments, because we have these unnecessary counterfactuals specified. But once we go to the partial environments, the vertices are exactly the deterministic environments, and there are just 4 of those in this case.
I have a question about that. So formally, the topological space is a quotient map, right? From the cube, we defined an equivalence relation to get this new shape. Now, I know how to define it topologically, but the question asks about the geometric properties, like the dimension and number of vertices and things like that. And I'm not sure how to formalize that in the language of quotients. Say how to think about the quotient shape as a polygon in space.
Yeah, that is a good point. I guess the dimension itself is preserved under this quotient because it's homeomorphism on interior. Yeah, I guess the vertices, they're not defined topologically, so maybe the question was a little sloppy in that way, but I guess it was, in light of question 2, it was a well-defined thing, because question 2 actually puts a convex structure on this space, and then we can talk about the vertices of it as a polytope. But that's actually a good point, that so this quotient map from the cube to the tetrahedron that we get here, so I guess the first and the second questions were maybe not entirely separate from each other. This. Should duck some of these. Okay, so here's a tetrahedron. It should have been direct. And so, for example, if we look at, I guess the thing I want to point out is that this map itself is not a linear map. For example, if we take this diagonal across opposite vertices of the cube, then it will go from this vertex to I guess the one in the back, but it actually goes through the middle here, the middle of the cube, so it actually goes through the middle of the tetrahedron, so it actually ends up being this kind of it's actually a second degree curve here, I think, which I think will also be maybe a bit clear from the question 2 why this is like a degree 2 thing, because we end up multiplying two things to get this map. So yeah, I mean, you can go into quite a bit of detail about this, but the main intention with this question was to just kind of give you an idea of the sort of rough shape of these spaces. But yeah, that was a good point I had, that technically the vertices are not defined in terms of the topology, but we would have to, or we can say that, you know, the vertices are defined in the cube, and then we can say whatever we end up after collapsing the vertices, we can call those the vertices of the tetrahedron. But yeah, it was a little, if you didn't consider the question 2, question 1 in isolation was a little underdefined, but hopefully it made sense to. Okay, so any other questions about this? Okay, so let me work out one more example, and then we'll move on to question 2. So let's look at the case where there are two actions, let's say A and B, and two observations. I keep them 0 and 1. So I guess in this case, we have to specify eta on the empty input, eta on the I guess 0A, eta of 0B, eta of 1A, and eta of 1B. These are different possibilities for the inputs of eta. So as again, the dimension for the entire maps and the partial maps is the same, which is in this case is 5, because there are five parameters here. So we're going to get a 5-dimensional space, and then again the same thing will happen, that if we just start with a 5-dimensional cube that has some redundancy in the specification. So the entire maps have kind of more information than they need to. And then once we collapse the additional information, then the remaining vertices are going to be just the deterministic maps, which I guess the deterministic maps in this case are going to be O cross O to the A. So the size of this is like 2 times 2 squared, which is 8. So there should be 8 vertices. And I'm going to try to draw a little sketch of this space. Of course, it's 5-dimensional, so I'm not going to be able to draw it perfectly in 2 dimensions, but hopefully this little sketch will give you a bit of an idea. So for one, it's useful to look at the restriction to the face where let's assume the first observation was 0. So in this case, what we're left with is actually just a two-dimensional space, namely specifying these two parameters. So in this case, we actually get a square here where this side is eta 0a and this side is eta 0b. So this basically says, okay, what is the probability of observing 0 versus 1 if the action was A, and what is the probability if the action is B? And these two are independent of each other, so we get a square here. And the vertices of the square are just, again, the deterministic environments, but with the first observation being 0. So here we get 0, and then I guess I'm using the same notation as before, but these correspond to the what's the output given A and what's the output given B. So here this is 0, 0, 1. This is 0, 1, 0, and 0, 1, 1. So this is what we have on kind of this side of the on the 0 side of things. And then if we look at the other side, which is when the initial output, the initial observation is 1, we again get a square. But I'm going to draw it sort of rotate it a little bit. And then here the vertices are 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So these are the 8 vertices of our polytope. And then the actual polytope is like, it comes with a projection onto the eta of lambda, where this square happened when eta of lambda was 0 with probability 1, and this side was when it's 1 with probability 1. And then in between, if you like end up connecting this up, so the way to think of this is that we have these two squares. You can imagine they sit in a 4-dimensional space, kind of orthogonal to each other. So the more relatable version of this was this like pink and blue line, which were the kind of front edge of this tetrahedron and the back edge, and then these are the axes for any slice in the middle. So we have kind of an analogous thing where I guess this green square is there. So the analogous thing here would be in the middle we would have some kind of like a 4-dimensional cube slice. I'll try my best to draw for a cube. So this would be the kind of slices in the middle, which is I guess you can think of this as the product of one of the squares times the other square. So basically that's why this is like a 5-dimensional thing overall, where it's parameterized by this one segment here, and then any slice in the middle is 4-dimensional. So overall we get 5 dimensions. Okay. I don't know if this like trying to build up the geometry is helpful to people, but
yeah, I think this is helpful for me.
It is okay. Yeah, I find that some people are just like think geometrically, and I tend to be one of them. So I kind of often think of these pictures, and for other people, this is like
Is there a complete description of the resulting spaces, like combinatorially?
Yeah, so you can yes, specify them completely as polytopes.
And it's an easy description, not like a bunch of quotients.
Yeah, actually, I guess Jean-Marie is still not here. It doesn't look like it. Yeah, I was going to ask him because he had sort of the most concise description of these, where you can give a recursive description where it turns out that, at least in the case where the size of O is 2 and the size of A is also 2, we actually get this recursive description that the environments up to time t plus 1 are isomorphic to the one up to t times itself. And there's a notion of join for polytopes, which I'm probably not going to define, but you could look it up if you're not familiar with it. So it basically ends up being this kind of thing. And in more generality, if you would have the number of a product over the number of actions here, and then this would be over the observations to join. So you can write down a kind of this full description of the polytope in terms of in a recursive way, and I think this is actually probably the simplest way to fully specify them that I know of. But this is an aside. I was not expecting people to write down this specification.
Does this also, like this, the general description with multiple actions and observations, also take into account like the possibility that like some of the observations will happen with probability 0, but not all of them? Like not deterministic, but like ruling out possible observations.
Sorry, I'm not sure I understand.
If there are more than 2 observations, then we could have like you said, we quotient at deterministic policies, but if we have more than 2 observations, then we can have stochastic policies that are still quotiented because they give probability 0 to observations.
Yeah, that's right. So it was, I guess, yeah. When we have to quotient that at certain kind of faces of the thing, not just vertices. Yeah, that's what you mean. Okay. So anyway, so this is sort of a geometric picture of what happens, but I guess the reason I was asking for just the number of the dimension and the number of vertices, because these you can easily compute just by computing the number of deterministic environments, which is the number of vertices, and then the dimension is going to be the same as for the entire map. So you can just add up the dimensions for the. Okay, so maybe given how we're doing on time, we should move on to question 2. And I was going to ask Ohad, would you be okay walking us through some of the main ideas that go into this?
Yeah, so I'll talk about the solution, and you write it on the book.
Yeah, that's the plan. Hopefully, I can keep up with you. And
okay.
I think we don't have to go into every detail. Just sort of maybe we can go through of how to define these maps and maybe what we would need to check to show that they're well defined, but maybe we don't have to go into the exact details.
Okay, yeah. So the first part of question 2 is about constructing an isomorphism between this structure for t equals 1 to the polytope that's defined on O times A squared. And yeah, and what I did here was given a partial function eta defined on O times A. I define a measure mu on the right set by explicitly saying for a sequence or O0, A0, O1, and A1. What is the probability to reach all of these observations? And so mu isn't a probability space in general because it's agnostic to the actions taken. It says like we don't care about the policy, but given that the policy shows these specific AI, which what is the probability that these observations are reached according to eta. And there's a specific formula that we can give here that is a product of the two distributions defined by eta. It's the probability of eta epsilon on O0. And then we multiply it by the probability with the context O0, A0 on the input O1. And here we need to explain that even though eta is a partial function, if the right-hand side is undefined, that's because the earlier probability is 0. So it basically that doesn't matter. The whole term collapses to 0. And yeah, so now from here we can prove that it satisfies the properties of the shape. That is for any given deterministic policy pi, the set that it defines has a total measure of 1. And here we basically do a double sum. And again, since the definition is quite agnostic in the actions themselves, it only relies on the fact that the two terms defined here are probability distribution. So we basically multiply two sums that each of them sum to 1.
So I guess.
So that defines the function.
So maybe we could write down just one example. Let's say the policy is something that always outputs action A, let's say. Right, and in this case, we'll be looking at the sum of mu O0A O1A, which I guess under this definition would be so this is a sum over O0 and O1. So this would be P mu lambda of O0 times P right, and then as Ohad was saying, we can this actually turns out to be just a product of the sums. Is this am I writing the right thing? And then, so because these are distributions, these are both equal to 1. Right? Is this what you were saying?
Yeah, that's it.
Okay. So this shows that this map is well defined. And okay. Question?
Yeah, can you hear me?
Yes.
Just to interject, I think this is a little bit more subtle because in your product, one of the sites depends on O0 in the very tiny index in ETA, so you can't actually write it like that. But
Yeah.
in principle, it works a lot.
Yeah. I think you're right. So basically, we would need to write it as kind of the sum of this. We can take out one of the sums like this, and then this is 1, and then afterwards we can sum this, and that would also be 1. So maybe this is better. Yeah.
So in this direction, this is something like using conditional distributions to construct a joint distribution. Is that correct? Roughly. If we think of this measure, measure is like an object, something like a joint distribution. Okay, I know it's not exactly a joint distribution, but it's the basic constructions here are something like the way a conditional distribution would be turned into a joint distribution.
Yeah, I think that's a reasonable heuristic. And then maybe one thing to point out is that, look, notice that we're multiplying 2 probabilities here, which is why we ended up this thing that I was pointing out, that this ends up being a quadratic degree 2 map in this way. So it's not linear. Okay. I give the mic back to Ohad if you want to continue.
That constructs the map in one direction, and then now we need to show that this map is bijective. So basically, given the measure mu, we write the defining rule again, but this time we try to show that given such a mu, there's a unique eta that satisfies these conditions. So yeah, here I don't have any high-level intuition to how to show this. Basically, I use the defining formula to construct eta explicitly. So it has 2 parts. We define eta on the empty input, and then eta for a pair O0 A0. And we can do it by summing over elements of mu. Yeah, if we have the defining product of mu that says that it's a product of 2 terms of eta, and we sum over one of them, then it cancels out to 1. And then we're left with only 1 term of eta on the left side.
Wait, sorry, I was not following it.
Yeah. Okay, so explicitly, what we get here is a sum over all O1 of mu of O0. And here I chose a specific policy arbitrarily, and just that it's O0, pi of O0, O1, and the pi of O0 and O1. And the reason to choose an arbitrary policy is because we need to choose some inputs in place of the A0 and A1, and if we remain consistent with a single pi, then we can use the defining condition of mu, that mu of c pi equals to 1, and then it shows that this actually defines a valid distribution.
Mm-hmm. And then it turns out to be independent of pi. It basically doesn't matter which pi we choose, but we can define it for any pi. It gives us the same.
Is that easy to show, that if you choose different pi, you get the same probabilities? That seems to be like quite a strong symmetry.
You're probably going to get it for free if you prove that they invert each other.
No, but you have to first show that this is well defined, right?
I mean, you can just fix the pi, like you can just say, like, take pi to be the constant,
yeah,
the one that outputs constant A or something.
Yep.
And then just plug that in here. So that's one way to say it, but then, yeah, I guess it's still good to know that it's actually independent of what pi is. And maybe I can just expand a high-level idea. For example, if you wanted to show, let's say that we take mu of O0 A O1A, and let's say we wanted to show that is this equal to mu of O0 A O1B, for example. So the way to do it is actually to say that this is equal to use this property that the output has to be the same, has to sum to 1 for any policy. So if we take the constant A policy, then it says that this should be 1 minus the sum of mu for all of the every other possible O0 tilde, O1 tilde. And then now, in this, there's also a policy which outputs A every time except on O0 and A1, O1 where it outputs B. Okay. So that should be equal to that one, and that way you can see that these two are equal. So maybe this is the simplest way to see that.
Okay, that's cool.
You would need to be independent of the policy.
Yeah, thanks. And Mateusz, I think you need to explicitly show this to prove their inverses. I don't think you can just claim their inverses without showing this. That's my instinct. Is that right?
Yeah, I think at some point you have to address this. Yeah, I mean you can push it to different points because you might be able to just define the map this way, but then you have to show that both of the compositions are inverse to each other. At some point, I think you have to write down this kind of argument. I think there's no getting away from it. Yeah, I think that's something that Felix pointed out, that some people kind of showed that, because I guess maybe that's a good sort of high-level thing to point out, that if you're trying to show that two maps are inverses to each other, let's say F and G, in general, you would have to show that F composed with G is equal to the identity on X, but then also show that G composed with F is equal to the identity on Y. So here there are two things one need to do, and I think Felix mentioned that people sometimes it's common to just show one of them, which I guess maybe was easier than the other. Yeah, there's a question.
Is there an easy way to see from mu what should the like the places where eta should be undefined are? Is there like a clear way to see that?
Oh yeah. So yeah, maybe I can let Ohad talk about the second part of how to define it here, and then I think that will be clear from there.
Yes. So for this part, we think of eta as basically the conditional probability that will give that O1 results, given that we already have this history. So here we can do mu on the entire tuple, like the probability of appearing of the appearance of O0, A0, O1, and A1, which is again arbitrary. And then we divide it by the prior probability that is eta of the empty string given on O0.
Right, and then this tells us that it's going to be undefined whenever the denominator is 0. So I think hopefully that answers the previous question. Yeah, thank you. Okay, and then so this defines the map backwards, and then as we said, for a kind of full solution, we would have to show that both of the composites are the identity to show that it's an isomorphism. And then so the second part of it was to show that so we already saw that we can include the deterministic environments inside of the stochastic ones. And so here we have this isomorphism, or I guess homeomorphism with the Pauli distributions. And I guess we're looking at the
by the way, why is the term Pauli distributions? Where does the word come from?
Oh yeah, that's a good question. That could be one. I think my intuition was just that it's not a distribution because it doesn't the total measure is not 1, but it is a distribution when restricted to any deterministic policy. So it's sort of like it's many distribution laid over on top of each other. Like for each policy, you get a distribution, but it's sort of like the measure captures all of those in like one place. So it's sort of a many distributions in one. That's why it's a Pauli distribution. That would be my intuition. I actually don't know if this term was invented by Vanessa or if it's commonly used. I learned it from her, so I don't know if it's a standard terminology. But I think it's an apt name. Okay, so quickly finish up here. So we have this inclusion here, which we can think of, since this is a polytope, we can think of it as including the vertices. Well, I guess, a priori, we don't know that these are the vertices, but this definitely gives us a map from distributions on deterministic maps to here, where we just extend via the convex structure to this is a free convex space on these points. And then the part of the question was to show that this is a surjective map, which is in general not injective. And so to show that it's surjective formally, it's actually, I think, not that simple. And I think maybe only Ohad gave a complete solution, if I remember correctly, but maybe Felix can correct me. But to give an intuition of what's going on here, I think it's useful to go back to this picture that I drew earlier, which was this square where we have eta of 0a and eta of 0b. So this gives us the possible outputs of the environment, assuming that the initial output was 0. And then we saw that the vertices of these are the deterministic environments. And then basically what happens is that if we take this simplex here, that's just going to be the simplex spanned by the deterministic environments, which is this tetrahedron on these deterministic environments. So this tetrahedron has 4 vertices, and it's a 3-dimensional thing. And then we see how it like projects down to the square in this way, where I guess the way I drew it is very suggestive of how the projection goes. But it's not injective. For example, if you take a point in the middle, which is 1/2 probability in each case, it actually corresponds to, it has like an entire line segment sort of here in the fiber. So for example, the mixture that's 0, 0, 0 plus 0, 1, 1 over 2, which would be on the kind of top edge of this tetrahedron, and the other mixture, which is 0, 0, 1, 0, 0, 1, plus 0, 1, 0 over 2. So those are 2 different points in the tetrahedron. One is on this front edge and the other is in the back edge. But they both map to the middle of the square. They just give the same mixed environment, which just gives probability 1/2 for each of the observations for each of the actions as well. So hopefully this gives kind of an intuition of why it's surjective but not injective in general.
So this polydistribution object here ultimately is a more, or I should say, a less redundant representation of what we're really trying to get at in this case.
Mm-hmm. Right, exactly. The space of partial environments or the space of polydistributions, which we showed, are isomorphic. Those are the kind of the exact description, like the non-redundant description of a stochastic environment. And then we can see how, so we can think of this as like, you can get every stochastic environment by just taking a mixture of deterministic environments. So that means you can flip a coin in the beginning of like which deterministic environment to follow and follow that one. And it's a non-trivial fact that you can get every stochastic environment that way. I mean, maybe it's somewhat intuitive, but it's a little subtle to show it exactly. So that's why it's a surjective map, but that's a redundant description where if we can mix these 2 deterministic environments or these 2, and we get the same stochastic environment as a result. Okay. Any other questions?
I'm always amazed at how broadly this this need for non-redundant descriptions of things applies across so many different branches of mathematics and other fields, but it's usually something that's tackled with mathematics. Very interesting.
Yeah, there's definitely a very common theme, maybe especially in physics, where there's like a whole area of gauge theory dedicated to like understanding redundancies of descriptions. And interestingly, I think the lesson over the course of history has been that redundancy is good. Like the more redundant the description, the better. But at the same time, I think it's useful to understand what the kind of the quotient of it is by the redundancies. So what the kind of actual thing specifying an object precisely is.
Yeah, one of the things, anytime you're trying to estimate something, And especially anytime that you're going to compute a derivative of anything with respect to one of these spaces, if you have a redundant description, then you'll have singular Hessian derivatives will go haywire. And also it's really difficult to define probability distributions over things that you don't have redundant, that you don't have non-redundant descriptions for. It's very, very interesting. Thanks, Lokesh. Agreed.
Yeah, so yeah, I guess we're at time, so feel free to go. If there are any kind of more open-ended questions or anything about in the course so far, can also ask us.
Are you open to questions about week 2 homework?
Sure. I'll try not to give any spoilers, but yeah.
Why wouldn't it be that a policy that solves a hypothesis class achieves 0 regret on that hypothesis class?
Well, so in general, a hypothesis class contains multiple hypotheses, right? And typically the optimal thing to do would be different under different hypotheses. So if you try to do the optimal thing for one hypothesis, you get 0 regret for that specific hypothesis, but that would typically turn out to be not optimal for another hypothesis in the class. So that's why learning is tricky, because you have to kind of optimize for all of the hypotheses that you're considering simultaneously. And, yeah.
Yeah, that's helpful. Thank you.
So in particular, I mean, a sort of high-level idea of learning is that as you take actions, kind of experiment and observe, you narrow it down better and better which of your hypotheses are viable, and then as you narrow that down, you kind of perform optimally with regards to the narrower set. And then in the cases of learnability, you can kind of do that in a way that in the limit your regret goes to 0. But that kind of requires your hypothesis to be somewhat forgiving, because I guess there was this example that we looked at in the last lecture where you take an action, and based on your very first action, you either go to heaven or hell, and you don't know which action does which. Then there's no way to learn that sort of thing, because you have to make you make a first action, and then you're immediately kind of doomed in one of the hypotheses, and then there's nothing to do about it afterwards. So that's why often for learnability we need some property of the hypothesis class that allows you to recover from mistakes, which is it's a topic of sometimes called traps. Like your hypothesis class shouldn't have any traps in order for it to be learnable.
trap is a like a formal notion. One can formalize this idea.
Yeah, I think so. I was planning to look at a bit at MDPs, Markov decision processes, on week 4, and for example, in that setting, it's quite easy to say what exactly a trap is. So we'll see a concrete formalization of it. Great, so maybe we can stop here and continue next week.
Okay, I have one more question.
All right.
I have you. So then, sorry if I just missed this in the lecture, but you have an expectation when you define the Bayes optimal policy. It's the argmax of the expectation of an expectation of utility. For the inner expectation, you're taking the expectation over the distribution defined by some particular eta and pi of u. But this u is like not a ut. There's like u, this is just like infinite time horizon utility, or I can't quite relate that u to the ut that is the basis of the definition of what it means for a policy to solve a hypothesis class.
Right, yeah, that's a good question, actually. Someone already asked about it in Discord, and I updated the homework to clarify this a little bit. So maybe check the latest version. But basically, you can define the Bayes optimal policy for any utility function. But when you're saying that something is learnable, we plug in the ut into the Bayes optimal, so we get a family of Bayes optimal policies, one for each t, and the task is to show that that family learns the hypothesis class.
That family. Gosh. Okay. I'll look at the.
Yeah, I changed the wording of the homework to make this clear. So I was like a little sloppy when writing it. I apologize.
Whoa.
Yeah, that's I guess generally I would recommend people like check the latest version of the homework, because I think this happened last week and this week too, where I read the homework and I think it makes sense, but then it turns out I forget a few things. So I tend to, like, after people ask questions on Discord, I tend to upload a new version with the fixes afterwards. So it's good to check back if you're confused about something. Maybe it was already clarified. Yeah, that's an issue with running a course for the first time, that there's a lot of mistakes to iron out.
Hey, no problem. No, I'm just glad that my question is reasonable. It's a relief.
Yeah, it's a valid question. All right. Yeah. Thank you, everyone. Then I'll see you next week.
Thank you
And
very much.
thank you, Ohad. Thank you so much.
Thank you.
Thank you so much for
Thank you,
presenting
Ohad,
and
presenting.
for everyone's homework. Very impressive homework submissions. It's really amazing.
Thank you. Goodbye.